So now that we've learned how to draw Lewis structures, I can actually show you examples of these exceptions to the octet rule. So first we have odd electron molecules. We call these free radicals, and the reason we call these free radicals is because you have that odd number of electrons on one of the atoms, they are going to want to react. So they will you can think of it like they will attack anything to get a pair of electrons to not have that lone electron by itself. So an example is NO2. Whenever you total the valence electrons for this Lewis structure, you'll get an odd number, and you end up having to place that lone electron on this nitrogen. So that's one of the possible examples of odd electron molecules. You'll typically see it with certain compounds with nitrogen. For the most part, you won't see too many more examples besides that. A very common other exception is electron deficient molecules. So these are usually group 2 or 13 atoms. Group 2 will have only 2 bonds around it, and then group 13 will have 3 bonds around it. So 2 bonds is only 4 electrons, and then 3 bonds is only 6 electrons around it. So both of these are deficient compared to like having an octet 8, but they're happy, so they're fine with it. Another example is hydrogen. Hydrogen will only have that duet that we discussed earlier. Here we have boron trifluoride. It only has 6 electrons around it, 3 bonds, and it's fine. It exists in that way. And then finally we have hypervalent molecules, or we can also call them expanded octets. These will be elements. So the central atoms that have expanded octets will be elements in the third period that have access to empty d orbitals, compared to anything in the second period or like above do not have access to empty d orbitals, because remember, d orbitals begin in 3D. There's no 2D orbitals. So anything in only like the second period or above, so first and second, they will not have access to d orbitals. So another thing I want to point out, or first actually let me show this example. We have phosphorus pentachloride. It has 2, 4, 6, 8, 10 electrons around it, but it's fine, it's happy. It can use those empty d orbitals for that. Now, something I do want to point out is that we will be drawing some compounds that involve noble gases. So this entire semester, I've been kind of saying over and over how noble gases are happy. They are fine with their number of electrons around them. They don't react with stuff. That's why they're called noble gases. So why have I been saying that? And now we have compounds with noble gases. So under certain conditions, noble gases can react. And this also has to do with the fact that the larger noble gases like xenon and krypton, they have so many shells of electrons that because of that, they kind of are very easy to ionize those electrons away. So just think of it, they have a lot and they have so many shells. Some of the electrons on the the valence electrons on the very last shell, energy shell, are so far away that the elements kind of don't really feel it. So there's just a lot of space in between there. So when they react, they're obviously sharing those electrons, but they're kind of like, meh, whatever, it's fine, I'll share them. So that's why you'll see some compounds that have xenon. And specifically, this xenon compound has an expanded octet. So it has 2, 4, 6, 8, 10 electrons around it. 3 of them are lone pairs, and then 2 are 2 bonding. So whenever we draw Lewis structures, you will find, hopefully, that there are kind of several different ways you can draw certain Lewis structures, and they are still following all those guidelines that we have set. So what happens, how do you decide which one is quote unquote the better Lewis structure? So we use some things called formal charges and also resonance. So formal charge is the hypothetical charge that an atom would have if you could redistribute the electrons in the bonds evenly. So that's like the textbook definition, but all you should think about formal charge as is how likely this type of bonding will happen. So we're going to talk about this when we get to molecular structure, but you will see that certain formal charges do not make that atom happy. So that means that that bonding pattern, or the way that it's bonded, will not make that atom happy. So it will prefer to be bonded in a different way, so a different Lewis structure. So all you really need to know is how to calculate it for now. So you will take the number of valence electrons in the atom, the number of lone pair electrons, and then half of the bonding electrons. So we're going to do an example together in the next slide. Go ahead and practice this. So we're going to assign formal charges to each atom in ICl4-. So this is a polyatomic ion. So first we're going to draw the Lewis structure. So this is good because you'll practice some more Lewis structures. And then we will calculate the formal charges for each atom in the compound. And then a guideline for formal charges is that the total charges must equal the charge. So the guidelines for just drawing Lewis structures were in the previous video, but just to refresh your memory, first we're going to calculate the total valence electrons. So we have 1 I. Each I is 7 valence electrons. And then we have 4 chlorines. Each chlorine is also 7 valence electrons because it's a halogen. And then we have 1 extra. So extra, just write it out however you want to do it. I like writing it out so I don't get confused. So this is going to be 35 plus 1, that's 36 total valence electrons available for me to use when I draw the Lewis structure. Next, you will draw a skeletal structure. So by that we mean we're going to figure out which one is our central atom. Usually, like I said, if you have one type of atom and then you have multiple of another type of atom, that one is going to be your central. So obviously I is our central, and then we're going to draw single bonds to our other atoms. So far, let's count up the electrons we've used. We've used 2 right there, 4, 6, and 8. So I just wanted to show you, but I'm going to erase that. So far we've used 8, right? We have a total of 36, meaning that we still have, 28 left? So our next step in the guidelines is to distribute electrons on the outer atoms so that they reach an octet. So we're going to do that quickly. I'm going to distribute lone pairs to all these chlorines. So I distributed those lone pairs, and if you count them up, it's a total of 6 on each of them that I distributed. So 6 times 4 is 24, so I have 4 valence electrons left. Now, where are those going to go? All the chlorines are happy, they all have an octet, and the next guideline is to actually distribute them on the central atom. So hopefully you notice that this is more than 8 electrons around that iodine, but that's okay because iodine has access to empty d orbitals, so it is beyond the 3rd period. So anything beyond the 3rd period or in the 3rd period has access to 3d orbitals, so they can have expanded octets, or we also call them hypervalent central atoms. So this is one of those exceptions, and basically that's it. We used up all our total valence electrons and we have our Lewis structure. Now we can calculate our formal charges for each atom in this compound. So first we're going to calculate the formal charge for iodine. Now something I want you to notice. Look at each chlorine in this compound. They are all identical. So every single chlorine in this compound has 3 lone pairs, right? 1, 2, 3, and 1 bonding pair. If they are all identical, you don't have to sit there and calculate individually. You can calculate the formal charge once, and then from there you can say, okay, all of them have that formal charge. So we're gonna only do this twice, which makes your life easier and will save you time on an exam. Okay, so for iodine, iodine has, if you recall, 7 valence electrons, so it's going to be 7 right here, right? Valence electrons minus the lone pair electron. So we're going to count up the lone pair electrons. So I have these two and these two. How many total is that? That's 4, okay? So minus 4, and then half of our bonding electrons. So let's count up our bonding electrons. So I'm erasing all this extra stuff, just get it out the way. So iodine has these 2, 4, 6, and 8. So 8 bonding electrons. So let's calculate that out. That's 7 minus 4, that's 3, and then minus that half of an 8, which is also 4, so 3 minus 4, that gives you minus 1. So the formal charge for iodine is minus 1. Now let's look at what this formal charge for chlorine is. So we have 7 valence electrons for chlorine as well. How many bonding electrons and lone pair electrons do we have? We have 2, 4, and 6 lone pair electrons. So keep in mind that for lone pair electrons, you're not counting lone pairs, you're counting the actual, how many electrons are actually within that, right? So when you have 3 pairs of shoes, you have 6 shoes, right? Not 3 shoes. And then half of our bonding electrons, which is only 2 right here. So 2, so 7 minus 6, and then minus 1, that gives us 0. So the formal charge for the chlorines is 0. Now remember, the formal charges must equal the charge. So we have 4 chlorines that are 0, and then we have that 1 iodine that is minus 1. And that makes sense because the charge is just minus 1. So that's how you would calculate formal charges, and just make sure that they equal the charge if there is a charge, right? Okay, so now we know how to determine formal charge. And next we're going to use that to help us predict molecular structure. So what does molecular structure mean? This is how the atoms will be arranged in a certain molecule or ion, and this will be in the most stable way. So this will be to maximize the atoms being happy. So you want as many atoms in your compound to be happy. So we're going to talk about what being happy means. So we will use these guidelines. So better structures will have fewer formal charges within them. Better structures will have smaller formal charges within them. So let's compare like something having a formal charge of +2 and something having a formal charge of +1. You're going to rather a structure that has formal charges of +1 compared to +2. So you just want smaller numbers. And then better structures will have the negative formal charge on the more electronegative atom and positive formal charges on the less electronegative atoms. So let's consider the Lewis structure for CO2. So I already have everything drawn out and all the formal charges calculated. So it would be the same process that we just practiced earlier. I just have it all right now just because it's pretty time consuming. So here we have CO2 written out 3 different ways. So we have OCO, OCO, OOC. So that's how they are different. But if you went and looked at the details of these, they are all following the octet rule. Yeah, they all have an octet. They all have the number of bonds that they need to form those octets. There's no electrons missing in any of these Lewis structures. So based off of those guidelines, these are all fine. So how do you determine which one is actually the most likely molecular structure? So when you calculate the formal charges for all of these, you're going to find that this structure has 0, 0, 0. This one's +1, 0, -1, and 0, +2, -2. Now we're going to use these guidelines about molecular structure to help us determine which of these is most likely the actual structure for CO2. So better structures have fewer formal charges. So right off the bat, we can tell this one doesn't have any formal charges, right? They're all 0. And then this one has 1 and 2 formal charges. This one has 1 and 2. So, you know, we kind of have a winner already, but let's go ahead and just look at the other ones. So let's rank them, right? So obviously this one is most likely our structure. And then next, better structures have smaller formal charges. So between this one and this structure right here has -1 and +1 compared to +2 and -2. So this one wins between those two. So this is obviously the most likely one. And then next, I mean, this one wins for sure, but between these two, if we just keep following the guidelines and we're like giving them hypothetical rankings, this would be second. And then finally, this last one, better structures have negative formal charges on the more electronegative atoms. So the more electronegative atom between carbon and oxygen is oxygen. Oxygen is way more electronegative compared to carbon. So you would want the negative charges on oxygen. And notice that here we have a -2 on this carbon. So that's a big no-no. Like, that carbon is not happy whatsoever. It's pissed off. So again, just showing you the different examples, but for sure this is the clear winner. It has no formal charges at all. This is the happiest version of CO2, so that's what it would actually look like.